I'm Ryu. I'm a PhD student with Danny, Alexander, and Antonio Comuniti. So in this talk, I'm going to talk about modeling uncertainty of human annotators and how to use such information to learn more effectively from noisy labels and in the presence of large disagreement. So, so this presentation is based on our recent work, which we will also present in CVPR next month. And a large component of the work was done during my internship at a startup called Butterfly Network. And we completed the work at UCL. And that's what I'm going to talk about today. So, right. So deep learning in the wild. So many practical applications of deep learning require learning from noisy labels. And the labels are typically come from multiple annotators of potentially varying skill levels and biases. And here's an example in the context of bird classification task. So the task is to classify images of birds into 3 categories of birds: Canada goose, red-necked grebe, and black duck. And David, who is a bird expert, can perform this classification task with 100% accuracy. On the other hand, Hannah, who is amateur bird watcher, tends to mix up American black duck and Canada goose. Even worse, Alex, who is a software engineer, is completely clueless about this and is unable to distinguish between any 3 categories of the birds. Right, and the training naively, learning from such noisy set of labels can pose an issue and potentially constrain the performance of the resultant machine learning model trained on it. Another important source of noise, which I'm not going to talk about, is input. So input images can themselves be noisy, how to interpret or nebulous images, but I'm not going to talk about it, and I'm going to solely focus on noise in labels, but not in the images. But we have done some experiments, and I'm happy to share after the talk if you're interested. So back to label noise. So the presence of large label noise can give rise to multiple issues. So first of all, garbage in, garbage out. So, naively training a machine learning model on highly noisy labels can constrain the performance of the model, which often necessitates data curation step. So data curation is known to be very time consuming and often suboptimal, and also turns out to be one of the least favorite tasks amongst data scientists. And this is also a big issue in radiology or medical imaging applications. So in radiology, we know it's been known that inter-reader or intra-reader variability is very high, and this is an established problem and can sort of introduce noise into the training data sets that we often train our machine learning models on. Right. And sort of the standard solution when preparing data sets or when training machine learning models on such data set is to take what's called majority vote, following the principle of wisdom crowds. So majority vote is quite simply the most representative opinion amongst experts. And this may not work. This is not always a solution. And particularly in medical imaging applications where the cost of label acquisition is high, first of all, it can be expensive. So acquiring labels from multiple many annotators can be expensive. And secondly, the sufficiently credible experts can be rare. So in which case, taking the majority vote could be completely misleading. So our attempt at addressing these challenges is the following. So the goal of this work was to sort of simultaneously model uncertainty or noisy behaviors of annotators and a true label distribution at the same time. In other words, we wanted to sort of come up with a way to separate label noise from individual annotators from the true label distribution that we wanted to estimate. And why do we want to do this? So first of all, we thought that this would enable, potentially enable automatic data curation. So if we have a good understanding of the sort of noisy behaviors of annotators, if we know exactly how each annotator makes his or her mistakes, then we can invert the mistakes to correct the noisy labels and then therefore train a supervised machine learning model on a cleaner set of labels and improve performance. And secondly, understanding of annotators can be informative or useful for future label acquisition too. So information about annotators can be useful in deciding, actually it's going to tell us, it would tell us which annotator is good at annotating what kind of data. And that would sort of potentially help us in deciding which annotator should be labeling, which new input samples. So here is a setup of the sort of more fundamental problem that we want to solve. So firstly, there are multiple annotators of potentially varying skill levels and biases. And we assume that each image in the training data is labeled by at least one annotator or potentially more. And we also assume that there's no meta information. So a priori, we don't know which expert has X number of years of experiences, or we don't know who is better than who in what categories of data. So we just know that we have images, a bunch of labels, and we know the identity of labels. So we know exactly which label came from who, but we don't know how good they are. And we also assume that we don't have golden data, which means there's no even a small portion of data we can trust or assume to be ground truth. And we're going to consider classification only. So, so I'm going to tell you about our model. So presented in this paper. And our model extends this ICML paper from 2009 in 2 ways. So firstly, we reformulated their model, originally proposed in binary classification to multi-class classification, which is quite trivial. And we used the CNN to model a component of the graphical model. Actually, specifically, we used CNN to model the distribution of a latent variable, of the latent variable of interest, which in this case is the true label distribution. And secondly, and more importantly, we proposed a simpler optimization scheme, which comes with a theoretical justification and is amenable to sparse labels. So what I mean by sparse labels is that each image is only annotated by a subset of annotators, not all necessarily. And I'm going to sort of show you some results later on that how our method performs, even in the case where there's only one label available per image, where the majority vote would completely fail. So specifically, our models the uncertainty or noisy behavior of each annotator with a confusion matrix. And the aim of this work is to sort of jointly learn the confusion matrices of the respective annotators and the true label distribution at the same time. Cool. So before delving into the details of the model, I'm going to tell you what a confusion matrix is. I'm sure you know what it is, but just in case. So confusion matrix characterizes the classification performance of an annotator. So in this case, so this confusion matrix shows that the annotator tends to misclassify durian as jackfruit 40% of the time in the first row, and jackfruit as durian 50% of the time, but the person always gets apples correctly. Right. And the model aims to sort of learn these confusion matrices of the annotators and try to separate them from the true label distribution, but purely based on noisy observations. So what does our model look like? So our model consists of 2 components. So first component is a CNN classifier, standard CNN classifier that we use to estimate the true label distribution. And the second component is a set of confusion matrices that characterize the respective annotators' behaviors. So each confusion matrix is assumed to be fixed per annotator and is sort of defined as trainable parameters that we learn during training time. And for each annotator, the distribution of each annotator is defined as the product of the estimated label distribution and the corresponding confusion matrix. Oh yeah, it's an hour here, right. And yeah, so in other words, each annotator's distribution is modeled as the corrupted version of the ground truth label distribution via the noisy channel of the confusion matrix. So we define the estimated annotator distributions for the other annotators, and then we then compute the cross-entropy loss between the estimated annotator's distribution and the real noisy labels that came from the corresponding annotator. So in this case, Y tildes, these guys represent the set of noisy labels from the respective annotators, and P of hat 1 and 2 and 3 and 4 represent the estimated distributions of annotator 1, 2, 4. And during training, we minimize the sum of the cross-entropy losses to learn the parameters of the CNN classifier and a set of confusion matrices, but purely based on noisy observations, Y tildes, and set of images. But there is an issue with this, with naively minimizing the cross-entropy losses. Specifically, this optimization is completely ill-defined. And that's because minimizing cross-entropy loss only minimizes the distance between the real annotator's distribution and the estimated annotator's distribution, but it doesn't necessarily separate the confusion matrix and the true label distribution. So in other words, given for each annotator, there are infinitely many pairs of combination of confusion matrix and label distribution whose the product is exactly equal to the ground truth annotator's distribution. So as a solution, we propose to add a simple regularization term, which is the mean trace of the confusion matrices of the annotators. So intuitively speaking, the mean trace represents the sort of the average probability that a randomly selected annotator is correct. So, in other words, so minimizing this trace term encourages the estimated annotators to be maximally unreliable, while minimizing the cross-entropy losses make sure that the model describes the noisy observations faithfully. And although I'm not going to actually, I had to sort of preclude it in the interest of time, but in the paper we just sort of try to demonstrate that if the noise in the dataset is sufficiently small, then minimizing this loss is a sensible thing, and is able to separate label noise from true label distributions, even in the case where you have very sparse labels. Right. So now I'm going to talk about results. So, particularly I'm going to focus on sort of illustrative examples on MNIST and ultrasound dataset that kind of well communicate the points that we wanted to make in the paper, but there is a more sort of boring and extensive analysis in the paper. So we used MNIST dataset to perform a more of a sort of controlled experiment where we have access to the real ground truth, and we can, where we can simulate a diverse types of different annotators with different behaviors. And we used a second data set to demonstrate the practical utility of our method in a sort of real world application. So on the MNIST experiment, we sort of simulated a diverse group of annotators of very different profiles. So actually 4 annotators, and I'm going to take you through one by one. So first of all, Alice, who achieves 70% accuracy, classification accuracy, and she has the characteristic of whimsically assigning random labels 30% of the time. And Andy, with average accuracy 60%, and he's not very good at discriminating similar looking numbers. So he tends to mix up, for example, 1, 7, 2, and 3, 6, 9, and so on. And so you see Carla, and she's not very good at discriminating labeling digits. So for example, 1, 2, 2, and 3, and etc. And Fading Frank, who has 0% accuracy, and he's a fundamental misunderstanding of what numbers mean. So he thinks 1 is 9, 2 is 8, and so on. Right. And we synthesized a bunch of noisy labels from these 4 people. And actually, in addition, we kind of assume that each image is labeled by only one annotator. So we randomly picked one annotator out of 4 for each image and get the person to label. Right. And we trained our method, and these are the sort of the set of recovered confusion matrices from our model. So although it's not perfect exactly, but it, the recovered confusion matrices clearly sort of show capture the main characteristics of the confusion matrices. Right. So, so once you've computed the confusion matrices, you can estimate the annotator accuracy as well by computing the sort of average of the diagonal entries in each confusion matrix. And the bar charts are showing the sort of comparing the ground truth and the estimates from our models. And the blue bars are the ground truth for respective annotators, and yellow bars show the results from the model that I've just showed you. And the green is the case where you actually have dense labels. So each image is labeled by all 4 annotators, not only one. And you can see that even with 1 label per image, the model is able to estimate annotator accuracy fairly well. So how about the classification performance? So we used the estimated true label distribution to perform the task of classification. And we compared against 3 baselines. So the baselines include the Oracle model, which is our model, but we assume that the confusion matrices of all the annotators are known to the model. And a naive CNN, which is simple CNN, trained on the majority votes. And Who Said What is sort of very recent model from Google, which performs similar sort of annotator modeling, but in a sort of with a slightly different model. And you can see that our model performs on par with the Oracle, while sort of outperforming naive CNN and the other model. We have, performed a lot more sort of systematic and detailed experiments on other data sets such as Cypher10. But so if you're interested in more sort of detailed analysis of detailed numerical analysis of this method for even more diverse, different sets of annotators, please have a look at the paper. So finally, we tested on the ultrasound dataset. So just to give you a quick overview of the dataset, so it's 6 classes, and it's sparsely labeled by 9 experts and 2 engineers. And we didn't have ground truth in this case, so we had to generate ones. So the way we generated some sort of pseudo ground truth is as follows. So we picked the top 3 experts based on their experiences. And then we only picked out the cases where these top 3 experts were unanimous. And then we removed all the labels from these top 3 experts, and then we trained our model on it. Right. And so this is the result. So on the top left is a plot between annotator accuracy and estimated annotator accuracy. And you can see that sort of the non-experts were clearly separated from the expert cloud. And the figure on the top right is there's some sort of pseudo ground truth confusion matrices compared with the estimates from our model. Interestingly, although the ground truth, we don't really have ground truths, but even with the pseudo ground truth confusion matrices, it is quite interesting to observe such a kind of high correspondence between the ground truth and the estimates, especially for non-experts. And lastly, it does improve the classification performance in comparison with the case where you simply train a CNN on the majority vote labels. Right. Got 1 minute. So summary. So one model, so we've shown that I think one model can simultaneously curate and learn from noisy data. in a sort of like, even with a diverse set of annotators. And successful recovery of confusion matrices can also visualize annotators' mistakes. And thirdly, it presented robust performance with sparse labels, which is much cheaper in practice. So there are various next steps, interesting next steps, and I'm going to focus on maybe a couple that I think are the most interesting next steps to me. So I think probably the first one would be model image dependence of annotators. So this is very important because in fact we assumed that annotators' confusion matrix is fixed per annotator and it's independent of the images, which is a very simplistic assumption. Clearly, obviously, an annotator's confusion pattern should depend on the image. So accounting for image dependence is quite easy implementationally, but validating it can be quite hard. But thinking about how you might want to do that is quite interesting and potentially useful, not only for more realistic modeling of annotators, but also I think it's potentially useful even for education and things. So maybe the second next step that I'm most interested in is how to integrate this annotator information into an active learning framework. So there are, clear way to kind of utilize information about annotators to decide which who should be labeling what examples and so on. And lastly, I'd like to acknowledge the contributors of this work. So Danny Alexander at UCL, who is my supervisor, and Natan Ardman Swami at Butterfly Network. Yeah, thank you very much.